I was always thinking to create a video on quantum technology and its associated measurement. It's very unfortunate that majority of the quantum measurement systems detectors are basically classical detectors, and many people have absolutely no idea that how the measurement is done. Measurement engineering and measurement physics is becoming a dormant, a very, very dormant subject of study. People hate it, they don't like it. And I have a deep pain and anger after 25 years of research that really it is going to be the future of the world. Are we going to really carry out absolutely nonsense and garbage measurement and then tag them as good physics, good engineering? 25 years back, when we were kids, we used to do the interfacing by ourselves, connecting an instrument with computer. It was one of the greatest thing. Lab view, and then even I started with elementary programming languages. Turbo. I mean, today's kids have not heard about this kind of thing. MS DOS programming, lines after code you write, type, and then uh, what we did in my PhD was we were always roaming around, and entire lab was automated. Indian Association for the Cultivation of Science in Calcutta, where I did my PhD, really we set an example. So 24 by 7, our instruments used to measure data, build the data, and plot the data. 2010, the I mean Cavendish Cambridge lab, I think, in UK came up with the idea of robot scientist, and they automated the whole lab. But we did it in 2002, and everybody used to ask, "Hey, why are you in the tea canteen?" We used to say that no, our experiment is going on, and everything was that. So what I wanted to say is that right from the scratch, you have to understand that every single instrument you connect to a circuit, to a device under measurement, all the instruments are connected, and simultaneously you need to calibrate all the instruments on a regular basis. On a regular basis, you need to collect the calibrate all the instruments, and this is called burning. It means it's a very high load measurement is carried out and exact with ideal set of values. Nobody understands. I need to teach. Even very famous professors do not understand that basically you measure potential. You call it a different name. For an example, I am measuring current. You never measure current. You measure voltage. You have to understand that you only measure power from which by calibration you give it a different name, whatever it is, whatever the physical parameters you have. And in optics, you measure light intensity. Whatever you say, I say phase, I say intensity, I say polarization, whatever it be the measurement, eventually you measure the photon count per unit time or potential, the power flow per unit time. And here is also power. So if power is the only measurement that you carry out, be it optic based, photonics based, quantum based, classical, whatever kind of measurement. And that's why that is the reason you need to understand. If you design, trying to invent a new kind of instrument, new kind of measurement system, you have to understand that entire system where the signal is generated and where the measurement is carried out, final measurement, all the steps, necessary steps, everything is coupled together. And you need to simulate in your computer the current flow in entire system and input output impedance matching for all the instruments who are connected in a singular circuit. And this was the first lesson given to us when we were doing PhD. And today's PhD students have absolutely no idea. Nobody tells them that all the instruments connected in the system is part. Now let's come to the quantum. Okay. So I will first talk about quantum optics. The reason is that I'm certainly involved with quantum optics works. This is 2:30 a.m. early morning in Japan, so uh, I was yawning a little bit. So one thing that you have to understand in quantum, in any kind of quantum measurement, is that SPAD, single photon avalanche diode, it is no different than avalanche diode, just in reverse bias. Okay, so can I use a avalanche diode for SPAD? Of course you can. Whatever it is, you are measuring light intensity, and if you are doing a quantum measurement, I want to measure quantum state of light. SPAD cannot do any quantum measurement. Whoever has told you doesn't understand instrumentation. Instrumentation is a subject, and it was there in India. Several institutes were created. They were shut down because who cares about fundamentals? You buy an instrument, connect it, your software gives you a result. You have absolutely no clue. Thousands of filters are connected to give you a beautiful result so that you are happy with it. And that's the reason majority of the technologies are never born. Not because the scientists don't have the knowledge. The reason why new inventions do not come is because the instrumentation, the software, so whom you are trusting, which are connected by as interfacing, they have hundreds and thousands of filters so that your instrument looks good. We rejected 150 years old of electroencephalogram EEG and replaced it with DGG, duodecagogram. One of the primary thing that I always say it, and I always say it and tell to my students, that always you have to remember that filter is a crime. Filtering data is a crime. You need to devise an engineering a protocol so that you can take higher order differential readings. Absolute measurement, that whatever you are doing is absolute nonsense. Absolute measurement is an absolute nonsense. Differential measurements, when you are starting not one layer, first order differential, second order differential, third order differential, when simultaneously measured, only then you can get the real data that you want to get. If you are having higher level dynamics on nonlinear systems you want to measure, if you do not have this kind of device engineering or characterization system engineering, you can never get. And today's time, more the time is passing by. Since 1970s, 80s, I have several instruments in my lab already, 1970s, 1980s, 1990s. The 30 years old instrument, 40 years old instrument, 50 years old instrument gives very good data, very calibrated, well established data. But the new kind of instruments in the chip that are coming, they use minimum analog and maximum digitization. When you use minimum analog and maximum digitization, you give the result of whom the person will be satisfied. So you understand that they need a 12-digit resolution. 12-digit resolution, you calibrate and you give 12-digit resolution. You can't. Your hardware, are you using that level of sensors? No, you are not using that level of sensors. What you are doing is basically cheating the measuring person, the experimental physicist. So in quantum, SPAD takes only measurement of intensity of light. And then you digitize it and you send it to the coincidence counter. And then coincidence counter measures the signal, and you say that, okay, from two different, you divide the light into two parts, and then it goes to two different light detector, SPAD. And from SPAD is go to the two channels of coincidence counter, and you say that you have done a quantum measurement. You have not. You have not. If you have a coherent current source and you have a coherent current detector simultaneously, and then it goes to the coincidence channel for current flow or photon flow. Photon flow, current flow is not a different thing in quantum, because in both cases, with sophisticated engineering, you have making sure that both the photon and the current flow are coherent. So when you are measuring with the SPAD or the coherent current detector, and then eventually you are sending it to a coincidence counter, you are doing purely classical measurement. So how can we bypass it? The problem is, in quantum, in classical also, but the classical it doesn't matter because all the variables are independent. In quantum, all variables are connected. Polarization, phase, intensity. If a classical wave goes through, then you do the measurement. Classical you do the measurement of intensity, polarization, phase, and all these kind of things. So so you can say that they are not interrelated, and if I do independent measurement, I can assume it. But in quantum, if you don't simultaneously measure all three parameters, then you are not doing a quantum measurement. Now, because many people, I mean, hardly any people understand quantum mechanics, then they say, can you simultaneously measure two different variables? Uncertainty principle will come in. Okay, you don't understand uncertainty principle. Don't talk nonsense. When you are doing measurement, even if you do polarization, even if phase, eventually you are measuring the power. So first you understand what you are talking about before making a nonsense statement. And do you measure wave function psi? You never measure wave function psi. Quantum tomography is basically a classical tomography. It is never a quantum tomography. Actual quantum states cannot be measured. You measure classical things. So how do we do it? Basically, what you do is instead of considering that the psi, where you have double derivative of space and single derivative of time, basically you take double derivative of space and double derivative of time, and then you do the carry out the measurement. That's how E is equal to E0 cos omega t minus plus minus phi. So you measure phi. Those who are doing sophisticated measurement, those who are, I mean, majority of the laboratories, I find that they have SPAD, they have a coherent current detector, and they have the coincidence counter. So to say that entanglement has happened. So majority labs, but there are good labs who understand quantum mechanics, and they simultaneously do the measurement. They also make big blunders, and that's why I'm making this video just to say that why it is critically challenging to measure quantum systems, and why only counted number of labs in the world are honestly doing the quantum measurement. Now see the situation. Uh, if you have three different parameters, say intensity, polarization, phase, all three things, I will simultaneously do the measurement. Then what happens is basically, say you take the light, photon, large number of photons are coming, a large number of coherent electrons are coming, you split it into three parts. That's not a problem. In quantum, you cannot create a replica, but dividing a large number of entangled photons into multiple different parts is not a problem. You just split it, it goes. Problem begins now. When you are detecting in the detectors, you think that once it enters, open the doors and enters inside the detector, because you are changing the properties a little bit. Because quantum is a tensor. It's a matrix like a square, and a lot of interactions and all their values superpose. So simultaneously, you need to change the condition for many, and you have to increase large number of sensors. And by providing large number of sensors, what you do is you change the condition for all of them and simultaneously carry out the measurement. So when you do that, you understand for one channel, a one wave function psi is going for one state, and you need to modify many phase values. Say E is equal to E0 cos omega t plus minus phi. So pi 1, pi 2, pi 3, pi 4, pi 5, pi 6. Then omega t you will be tuning. E0 you will be U1 or E0 or polarization vectors. But that one also you will E1, E2, E3, E4, E5, E6, all like this. And then the intensity, because I square E square Now E, you say, I measure E, so why should I measure E square? Yeah, in quantum, you have to do it. Yeah. There is no escape from that. So when you are doing it, you are putting different kind of values, because with every different values of phase, the U1 will change. For every phi, you will change, and I will also change. So all these three, if you have an array of say 3 cross 7, 3 cross 8, 1, 2, 3, three variables, and 8 different values. That means 24 channel coincidence count, 24 channel SPAD. 24 different SPAD is required at least to have 8. Why 8? 2 into 22. And basically, if you really want to do the measurement, then you should have forecast flow, that is 16. So 3 into 16, 48. If SPAD counters are there, then you will be in principle be able to see the whole picture of the quantum. But we do not have the money. When we do not have the money, then we find a physics way how even a few measurements with a clever trick. And that kind of paper also come out in reputed journals with a peer reviewed by the greatest scientists. And then they say he devised a very clever way. Earlier you needed 48 sensors, now you need only 3 sensors, and you can do it. That's Forget that. Let's get into the real business. So imagine for measuring all 3 parameters, you are putting array of sensors. Okay. So earlier you had only 1 SPAD or 2 SPAD for entanglement measurement. Now for each one, you are having 3 into say 16, because I would like to forecast for a quaternion. I would measure for every single values. Then you can correctly get. Even then, there is a problem. The problem is when the signal is dividing into multiple parts, 48 different parts, and going to 48 different sensors to create a tensor of particular quantum state that is going through one channel, and for other channel again 48, to total 96 for 3 values, polarization, phase, and intensity. 3 values you want to measure simultaneously. You want to get a data. So 96 sensors you have put. Now the problem is, if you have all these kind of sensors connected, you consider that when I'm changing the value 5, 1, 5, 2, 5, 3, 5, 4, and then putting it over there with a particular polarization gap, you can use many kind of SLM or other kind of phase modulation devices. You can have intensity modulation devices. You can have photon counting temporal sensitivity. And that is for different eye, you get 8 different values or something like that. So different channels you have, and you would think that all the channels are measuring it classically, and you really do, because if you are doing the measurement, then none of the other sensors you can see. This is true for classical. And this is where I am very disturbed. And I feel I very much dislike many of the quantum science engineers who are doing the measurement. In quantum science, each and every sensors, when you are measuring, they can see each other. So all 48 sensors can see each other. And all 48 sensors and their condition that you are changing them, and you suggest, and non-demolition type measurement without changing the state. That's kind of absolutely bogus and nonsense statements, and you find in Nature Science journal even they publish. How and why, I don't have no idea. I can do the measurement, but the state will never change. Uh, Measurement changes the state that you teach the kid, and you do not follow it when you come to the laboratory, just because you have to do the measurement and still you have to take the signal out. So you take part of the signal, and when you are doing the measurement, then other part of the signal has no clue. That's why you are able to measure 48 different signals. No, 48 different sensors and modification systems, whatever they are. All together, the geometry of arrangement of sensors become an operator, and that operates on the input function. So when you are doing quantum tomography, be very sure that you are taking psi into measurement system operators, K, and you are getting it output as psi dash. How to get rid of it? Nobody has any interest. But now from one sensor, earlier you were going sending out only one output to the coincidence counter. So for 16 channels, um, again another absolute garbage that you hear from the top class quantum science engineers, that I have made 5 qubit system. I have made a 12 qubit quantum computer. Come on. If you do multiple measurements with multiple different divisions and centers, and then you do not use a proper quantum machine learning algorithm to simulate the operator generated by the measurement system architecture. Have you done quantum machine learning? I don't know anybody. I have so far not met a single quantum engineer who does this. Because today's time, instrumentation engineers have absolutely no connection with the physicist. 25 years back, when we were doing our PhD, at that point of time, even in India, there was a huge, and instrumentation engineers or professors were highly respected. In today's time, you go to any IITs or any top institutes in the world, you will hardly find instrumentation engineers are an integral part of a physics laboratory or biology laboratory, or any laboratory where advanced level of measurements are carrying out. So this operator is generated by the geometric arrangement of the sensors that is never ever evaluated by quantum machine learning algorithm. Their systems are never optimized. This is the situation of at the top laboratories. But a bad laboratory means one sensor and they send it to the coincidence counter. If you have 5 different qubits and you have connected and created 5 qubit quantum computer, you are a liar, you are a fraud, and you have not understood the fundamentals of science. If you want to understand quantum mechanics, you need at least a quaternion, that is 4 cross 4, 16 channel sensor. So 16 channel, this simultaneous measurement has to be done. So you buy from the market 16 channel coincidence counter. There are companies who sell that. And you do the simultaneous measurement. Now this question comes that you need to do simultaneous measurement of multiple different parameters to understand the single decision that you are making. That means even in the worst case scenario in your laboratory, the SPAD should be modified and there should be the SPAD associated circuit. Forget about it. Say many SPAD assembly. Just one state you are measuring. So you have divided into 2 parts, entangled part. One part I'm talking about. Before you do the entanglement measurement, superposition measurement, or whatever. Now, this channel, so order in calculation, order in measurement, and all this kind of quantum metrology, people are doing it. I'm not blaming them. They have to publish their papers and they have to get their bread and butter. But say from the coincidence count, from the SPAD, or from that detects a single photon, you take out 3 output. Now, what will be the situation? In coincidence counter, for one SPAD, you should have at least 3. Okay, so a very clever solution is needed, because coincidence counters are not, in today's time, coincidence counters are not designed to do that. So we opened the coincidence counter and then we saw what is inside. It's pure classical measurement circuit that is inside. You will see sensors are coming in, and then independently all the signals are being processed. There is nothing quantum inside coincidence counter. I do not want to name the company. It is one of the best company in the world, with picosecond, sub-picosecond, or around 1 picosecond resolution. That instrument I'm talking about, when we opened, it's not a nanosecond coincidence counter, which are available in the market in $40. I'm talking about about a $40,000, $50,000, or $80,000 coincidence counter. So one of the most sophisticated ones that are available in the world. Even those systems, there is no provision for quantum mechanics. So I do not want to delay. I do not want to go into details. I just wanted to say is that order in measurement, how many channels you need to divide. Just dividing those who are publishing in quantum metrology, top class nature science papers on quantum metrology, when one channel to multiple different channels, dividing it, uh, even then they are significantly compromised with their system when they are doing the measurement, because you need to do back and forth many times measurement. In today's time, for quantum tomography, you consider Wagner function, you do repeated measurement as if you teach kids that quantum states are, could be generated simultaneously. You generate it, it is built, but if you do it multiple times, you cannot generate an identical quantum state. Why you see identical? Because classical measurement is continuously carried out in all over the world. You have two coincidence counters going side by side, and if you want to see coincidence, you can see coincidence, because in a laboratory, what is the separation, physical separation between the two sensors? So you need additional calculation systems. But what you are doing is you are doing repeated quantum state measurements, and you are showing that by repeated measurement, I'm increasing the probability. First, you take noise at as the signature of quantum uncertainty. Quantum uncertainty is not the noise of your laboratory measurement. I am really, with this video, I would like to say, if any scientist uh, can tell me that they are not measuring the laboratory noise, they are measuring the fluctuations because of the quantum only, I would love to come and see their lab. The reason is that I will come from my own money, because I believe that such a system has not been built. And there should be a serious, sincere discussion on differential measurements to get the higher order G values simultaneously in the infinite series in a multiple higher order measurement. So that discussion I do not want to get into, because we would definitely, certainly like to patent the technology that we have developed, and we want to make it a very novel practice to do it. I'm not saying that we are also measuring quantum state in a very absolute with absolute credentials. No, because quantum state cannot be measured until people understand how quantum state is born and what is the nature of a quantum state very clearly, because we have not derived quantum mechanics. It is just observation, and we know that there is a secret source of quantum mechanics which gives us a projection in the classical world. So by looking at the projections in the classical world, we create a branched idea with transfer matrix of different local points, and then we consider it. However, in future, definitely a real technology will come when we will be able to do the measurement. But until that time comes, when we understand quantum mechanics, the situation that we have is grim. Grim in the sense is that majority of the people who are doing the quantum measurement are doing the pure classical measurement, measuring pure classical noise and reducing the classical noise to increase the fidelity, and publishing papers in very good journal claiming that they have received 99.99% fidelity or 96% fidelity. This whole fidelity business that is going on in the name of quantum measurement, you will see that they reduce the classical noise in their laboratory measurement setup, as if I reduce the noise of my classical measurement or quantum measurement setup, and then I will be able to see the quantum. First of all, how many hyperspace have you invented? Hyperspace engineering. Higher dimension is not quantum, it's classical. And I'm tired of explaining this to many professors, that higher dimension is not quantum. Hyper dimensions are quantum. And hyperdimension engineering requires proper engineering, complete understanding of quantum mechanics. Complete understanding of quantum mechanics has not been done because we need to understand that we need a higher level mechanics from which the principles of quantum mechanics could be derived. Only then we will be able to understand. Until then, even those great laboratories who are doing the measurement needs to go through further refinement and further technological advancement. Unless until that happens, none of the measurements are actually taking the whole picture or the true picture of a quantum state or psi. So repeated measurements, reducing laboratory noise or experimental set of noise are not enough. Higher order differential signal measurement, and then with quantum machine learning algorithm, um, do that. And for that purpose, optimizing the geometry of sensor arrangement is necessary. That's why we have to go to rank 3, order 3 tensorial 3D tensorial system, and a massive infrastructure for the graphical information processing for those three-dimensional tensors is necessary to understand even partially a quantum state. And I would like to end with this. Probably only a very advanced level of quantum computer would give us an advanced level of quantum sensor, and that would evolve itself. Like we are waiting for the human intelligence G, and that will give rise to G plus, and then that will give rise to G plus plus. If there, so a artificial brain will be the last machine made by mankind, because then G plus and G plus plus automatically make. Similarly, there will be quantum, the first quantum computer, proper quantum computer with all these differential signals and higher order measurement with massive investment. So you can understand, even for 2 channels, if you have 96 different sensors and you have 96 channel coincidence counters, then you will be able to regenerate. No. Even then you will not. You need to do the differential engineering so that all the G values, higher order G values, are measured simultaneously. Only then you can have little idea of the quantum state. If you have any quantum computer, anybody builds, I don't know who will invest this money. A global mission is needed for such project. And if we do this kind of the kind of measurement or this kind of system, then we will be able to create quantum computers. And that quantum computers, that quantum sensors, if they are miniaturized and small, and then many tiny units of it all around the quantum computer, will give us a better and a better and a better. So quantum first ideal quantum computer, C, QC plus. So that quantum computer will give rise to QC++, and that will give rise to QC++, and eventually one day we will be able to understand what is quantum mechanics.